Hello friends, so let us continue. In the last session we saw how we have taken moments across the y-axis. Now we will try to see the moments about the z-axis. So let us have a look. The components that are taken in z-axis are px, py, q, b and the frictional forces. Okay, so let's try to have a quick visualization first. So here is the visualization. So again drawing the xyz axis. So here is your x axis, here is your z, and we want to take moments about the z axis only. Okay, so what are the components that would have moments about the z axis that would be having a certain distance from the z axis? Okay, so if you see from the top, there are various components which have a distance from the z axis, and the first and the foremost being the forces themselves. Okay, so here the forces that are coming from the tool, okay, they would be px and your py. Okay, so unless exactly they are sitting on the z axis, which is not true, because if you see the point here, it is having a certain distance from the z axis. Okay, so your px py would have the components, and you would be able to see them clearly in the two-dimensional image, which will come to in just a second. So px and the py would have a certain distance from the z axis. Now let us see which other forces we have. The other forces which would have a distance would be the frictional force F times C and F times B. Okay, so these forces have a certain distance from the z axis, and therefore they would contribute to the moments. Also this force Q, okay, so this force Q itself has a certain distance from the z axis. Okay, so that distance would have to be calculated, and that distance would create a certain moment. Okay, and obviously there would be the horizontal force B. Okay, that would act at a certain distance xb from the plane of the yz axis. Okay, so therefore that also would give you a certain distance. So essentially we are taking those forces which are having a certain distance from the z axis, also we can say from the yz plane. Okay, so that is the force that we have to consider, and that would create a certain moment about the z axis. Okay, now after understanding how frictional forces etc can have moments, we can go back to our 2D diagram to further investigate this. Okay, so here is our two-dimensional diagram, and here we seem to have our z axis right here. Okay, so the force first component is your py force py. Okay, so this py force acts here. Okay, this py force is acting right here, and it has a distance of xp, okay, about the z axis. So if you see from the top, that force would have basically a clockwise moment. Okay, so this force is coming out here, and it would, when you look from the top, it will have a clockwise moment. So we'll write here py times xp. Okay, then there is also the force which is in the x direction. Okay, which is seen right here. Okay, so this force is seen in this image right here. Okay, and this force px would also have a certain moment, and that would again be basically clockwise about the z-axis. So we would write here px times uh, the distance that is there about the x-axis. Okay, and we can see here that that distance is given by right here, the distance yp. Okay, so let us go back to the previous slide here, and here you can see that is the distance from the x-axis. Let me yeah, so it's right here, px times yp. So we can say here that's the second component. After having this component, we go to the next one, that is the q, the force component, which is called q. Now this force q, which is seen in this image right here, which is about the lead screw, that would have this distance yq. Okay, and that yq component, when looked from the top, basically that would give again a clockwise type of moment. Okay, so we can say here this is q times yq. Okay, now when we try to see the other moments, we can see here that there are some other moments along with this, and those moments are basically the frictional forces. Okay, that are coming here. Again, they will be seen as dots. Okay, so those frictional components, they would give you the moments about the z-axis also. So the frictional components would be F times C. Okay, and that acts at a distance of B, and plus C by 2. Okay, so yeah, that would act at the distance of B only. And then there would be a force component which is acting in this phase, which is going in the depth direction, which is opposing this, and that would be B plus C by 2. Okay, so those would be the components, and they are also part of the moment equation. Okay, so in this particular way, we can see here that all of these components ultimately add up here, and the moment equation is formed here. Okay, so here we see your px yp is there, py into xp is there, your q times yq is given. Okay, so I think the direction of q that has been assumed is in the opposite direction, so therefore it is coming inside the anti-clockwise moment, which is understandable. Similarly, b times xb would be one of the components, which is the component because of the force b, which is the reaction on the vertical face. Okay, so that is also not at the center, so also that is being assumed in the anti-clockwise direction. And then finally the last two components are the frictional force, that is F times B, that is the frictional force on that vertical surface, and the distance it acts is B plus C by 2. Okay, so one has to note that that C by 2 is in the bracket and B is outside the bracket, so that is a misprint. So it should be F times B, and the distance would be B plus C dash by 2. That's how it should be. So please make a note of this when you do your various solutions. Okay, and the last component that we have here is F times C times B. Okay, so that is again in the um, clockwise direction. Okay, so if you had to sort of have the top view, your z axis would look at this point. Okay, and then we would basically see that all forces which were clockwise, for example this is the friction component because of your your FC right here, then there would be the friction component because of B, then there would be the px component right here. Okay, py component right here, and so on and so forth. Okay, so the px component would be seen here, py component would be seen here, so all of such components would get the clockwise direction. So with this you can have a sense, and you can do your practice and set up these moment equations. um, just one thing, note that this bracket c by 2 is together, so b plus c by 2, that is the only typo in the book that we can see here. uh, so that is something that has to be noted. Now one important thing here is that these two equations are already there. Now the third equation we are compelled to see and take the equation in terms of the x moment about the x axis. Okay, which is given right here. But the problem with this equation here, sigma mx, is that it does not have any of the xa, xb and xc components. Okay, so that is a big issue, and therefore that equation really does not help. We have got three equations and we need to have three unknowns. Okay, so if you see carefully in this equation, you have seen xb comes here, xa comes here, and xc comes here. Okay, but we need a third equation which has xa, xb, xc. Okay, so that equation is not here, so therefore a type of assumption has to be made, because we are trying to solve these problems which have to be statically determinate, so that is very difficult. So therefore an assumption is made here, and that assumption has to be understood well. So what that assumption states is that additional equation may be written by assuming the moment of the reactive force A and C about the y-axis is proportional to the width of the slideway face. Okay, so what they're saying is A times XA by C times XC is equal to A dash by C dash. Okay, so this is the third equation that they are giving us. So, and this also seems pretty okay. A times XA and C times XC can be attributed to the widths and the reactions. So let us look into the diagram here. Okay, so what we are saying here is whatever the forces are there, just a second. So suppose you've got A and the distance from the center is XA, and similarly you have got C and the distance from the center is XC. So what you're saying is this proportional is proportion to these widths. Okay, so that seems to be pretty logical also. Many times it happens that XA and XC can be almost equal, and also the widths of the slideways they are also pretty much very times similar. Okay, very many times similar. So this equation would yield a proper result. Okay, so that should not be an issue. So solving these equations 4.25, 4.26 and 4.27, the values of XA, XB and XC can be determined. In the next session we will see how to from these values XA, XB, XC how to ultimately determine the type of pressure pattern that is developed on each slideway. Thank you.